Welcome to Business Statistical Analysis video number 27. Hey, in this video, we got to talk about the binomial probability distribution and the amazing Binom.DIST.RANGE function. We'll also plot the distribution in a chart. All right, we're going to start in page 13 in our PDF notes. And right off the bat, we're going to look at the binomial probability function. Now, that function looks big and scary, but we're going to try and break it down piece by piece and understand it. Even if you don't understand it, it's going to be a lot easier to use a formula like this, or the Binom.DIST.RANGE function that we'll use. That's an Excel function. It's easier to use those than do what we did earlier in this class, which is list all the sample points and then add all the probabilities for a given event. Now, before we can use that math formula or our Excel built-in function, we got to talk about what the requirements for a binomial experiment are. Number one, the experiment consists of a sequence of n identical trials. The random variable counts the number of successes in a fixed number of trials. And fixed number of trials will be represented by n. 2, there are only two outcomes possible on each trial. One is defined as a success, the other not success or failure. 3, the probability of success denoted as p, or in other textbooks, you might see pi. That has to remain the same on each trial. And the trials are independent. Now let's scroll down and look at some examples. If we have a salesperson who makes 4 sales calls, and each call ends up in a sale or not a sale, and from past data we know that the probability of making a sale is 0.2, do we have a binomial experiment? Well, fixed number of trials, that equals 4. We can define success either way. We'll define success as a sale, the p, 0.2, and it remains the same each time. And is each call independent? Yes. So that's a binomial experiment. How about a test with 15 true-false questions? Well, is there a fixed number of trials? Yes, there is, 15. How about a success or failure? Yeah, you either get it correct or not. We'll define it as get correct. And is the probability the same each time? It is for both options, 0.5. And is each trial, the answering of each question, independent? Yes. So that's a binomial experiment. How about flipping a coin 3 times? Well, we have a fixed number of trials, 3. Success can be head or tail. Probability for either one is the same at 0.5 for each trial. And yes, each coin flip is independent of the other. So that's a binomial experiment. How about if you're interested in whether somebody gets stuck in traffic, is driving across a bridge 7 times during rush hour traffic? Is that a binomial experiment? Well, n equals 7. We can define s as stuck in traffic. From past data, we know that 15% of the time there is traffic. And yes, from day to day, we can assume that getting stuck in traffic on one day is independent of getting stuck in traffic on another day. So that's a binomial experiment. How about if we're interested in whether an airplane is late or not? Is the experiment air flight from Oakland to Seattle, 6 flights per day, where we know from past data that the probability that any given plane is late is 10%. Is that a binomial experiment? N equals 6, 6 flights per day. We can define a success as late. The probability is 0.1, and it stays the same for each trial. And yes, we can assume independence for each flight. For all of these experiments with the simple n input and a known probability of success, we can use the math formula or the Excel functions to calculate our probabilities. Now, to see why our math formula actually makes some sense, let's scroll up to page 8. Now, to understand why that math formula works, let's go back to chapter 4 adding and multiplying laws. Remember, adding is an OR logical test, and multiplying is an AND logical test. Now, here's our example. An insurance agent has appointments with 4 prospective clients tomorrow. From the past, she knows that the probability of making a sale on any one appointment is 1 in 5. What is the likelihood that she'll sell 3 policies in 4 tries? So we have the event, sell 3 policies in 4 tries. The question is this a binomial experiment? Well, we have a fixed number of trials, 4. There are only 2 possibilities on any trial, sale or not sale. Each attempt at a sale will be independent, and the probability, 0.2, remains the same each time. Now, x, the discrete random variable, can take on the values 0, 1, 2, 3, or 4. Now, if we scroll down, here's how we did it in Chapter 4. We had to get busy creating all the sample points. So sale, 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 not sale. Sale, sale, not sale, sale. So we listed all 3, and then we had to figure out the probabilities. And notice, this is multiplying. So really what we're doing is we're saying, for this sample point, what's the probability of getting a sale and a sale on the next try, and a sale on the next try, and not a sale on the last try. So we multiply, and there's the probability for the sample point. And then we repeat that for the next sample point, sale, and not sale, and sale. Because we're running an AND logical test, we multiply, and guess what? We get exactly the same sample point probability. Now, when we continue doing this, notice that because we only have 1 not sale, there's always going to be 1, 2, 3, 0.2 probabilities for sale and 1.8 for not sale. Now, when we run the AND logical test for every sample point and calculate the probability, then down at the bottom, since the definition of a probability of an event is to add the probability of all the sample points, we simply add. And this is really an OR logical test. It's what's the probability of getting this sample point, or this one, or this one, or the 4th one. So there's our probability for 3 sales in 4 tries. Now, that may be fun to do longhand like that. And certainly, it's awesome to see how a probability is constructed from sample points. But really, I'd rather use that math formula. Now, to understand why that math formula works the way it does, let's notice some patterns about these sample points. Notice that every one of the sample points has the same number of probability of successes. That would be 3. And guess what? That 1, 2, 3, that's always going to be the x value. And for each sample point, the probability of not a success, well, it's exactly 1 for each sample point. But how do we calculate the 1? Well, guess what? You take the number of trials and you subtract the x value. Now, the only thing missing from our formula is how do we calculate how many sample points there are? Well, we're going to scroll down and see. And when we scroll down, there's something big and scary on the next page. Oh, man, that's every single sample point for trying to make a sale 4 times. We definitely don't want to do that. But when we scroll down, there's the last bit we need for our formula. That's the formula for number of combinations. That'll give us the number of experimental outcomes, our sample points, that provide exactly x successes in n trials. So if we scroll down, here's putting it all together. We have probability of success, probability of not success, x and n. Well, that would be 4 times those probabilities. The 4 is going to come from our combination formula. The probability of success raised to the 3, that's always going to be p raised to the x value. And the 0.8 raised to the 1, that's always going to be 1 minus p raised to the number of trials minus the x. So that's the binomial probability function. If we were going to do it longhand, these are the steps we do and we'd get exactly the same probability. Now, page 13 in our PDF notes shows the full formula and the variables. Now, Binom.DIST, this is a binomial probability function that we've used for decades. And these are the arguments, but we now have a new amazing function, Binom.DIST.RANGE. The trials argument, that's where we'll put our n. Probability underscore s, that's the probability of success. And number underscore s, that's where we put our first x. And if we put just one x in number underscore s, Binom.DIST.RANGE calculates the probability for exactly that x. But if we give it two x's, the smaller x and the bigger x, Binom.DIST.RANGE will calculate the probability between the two x values inclusive. Now, before we go over to Excel and try this, we have one more thing we want to look at. Page 15, expected value and standard deviation. Now, we know how to calculate expected value and standard deviation from a probability distribution. But if you only have n and p, look at that. N times p gives you expected value. And the square root of n times p times 1 minus p, that'll give you the standard deviation. All right, let's jump over to Excel and try all of these exciting things. All right, we're going to start on the sheet B1. And we want to calculate the probability of making exactly 3 sales in 4 tries, the sample point, math formula, and Excel function method. Now, I've already listed the sample points, 4 of them here, and the probabilities of success and not success for each sample point. We're going to multiply, and so we're going to use the product function. In the number 1 argument, we just highlight those 4 numbers, and it will multiply each one in succession. Close parenthesis, Control Enter, and then copy it down. If I look at the last cell, F2, it's got the correct spilled range from H15. Now we want to add Alt equals, and when I hit Enter, I get the 2.56%. This is the probability of x being exactly equal to 3. From the sample point method, it really is probability of sample point 1 or sample point 2 or 3 or 4. Now the math formula. We'll start out by using the combination function. The number, that's the number of trials, comma, number chosen, that's our x. If I close parentheses and Control Enter, I have a 4, F2. Now we need to multiply by the probability of success raised to the x. And then multiply that times 1 minus probability of success, close parentheses. And we need to raise it, and we have to do subtraction first for the exponent. So in parentheses, number of trials minus x. And close parentheses, that's our formula. We get exactly the same thing. Now let's try Binom.DIST.RANGE equals Binom. There's the old function we used, but now we have this one with the range at the end. And the advantage to this function is we're allowed to put in a single x or 2 x's. All right, number of trials, that's n, our 4, comma, probability of success, there it is, comma. And we only use number underscore s to get our x because we're calculating the probability for exactly that x. Now when I hit Enter, I get exactly the same thing. Now let's go over to the sheet B2. Now for the insurance agent problem, we want to do a few things on this sheet. First, we want to build the full probability distribution for this experiment. Then we want to chart it, calculate the mean and standard deviation, and calculate various probabilities. Now for this insurance agent problem, we already checked to see if it's a binomial experiment, and we answered yes to all 4 conditions. Now, with a fixed number of trials of 4, the possibilities for x are 0 to 4. So in the top cell here, we'll use the sequence function. We've done this a few times. Rows, well, it's 4 plus 1 for the 0, comma, skip over columns, comma, and the start is 0. We don't have to put step in because sequence will automatically increment by 1. So when I hit enter, there's our x values. Now here's how amazing this new function is. Binom.DIST.RANGE. We're going to put trials, comma, probability, comma, and for number s, we simply put in our spilled array of x values. In Binom.DIST.RANGE, we'll calculate the probability for each x. And when I hit enter, there's all of the probabilities for this experiment. Now we have to check if our two requirements for probability distribution are met. Alt equals, they better add up to 1, and they do. And each one of these is greater than or equal to 0, so both conditions are met. Now to plot the distribution in a chart, we highlight the label at the top and the probabilities. Insert charts. We'll select column. Move it, and the very first thing we do is we get rid of the default values. We need to add our x values. So right-click, select data, edit, highlight the x values. OK, OK. Now let's add axis titles. There's the probability. I see it's highlighted with a solid line, so I type an equal sign. That jumps me up to the formula bar. I'm going to select B17 and enter. Axis title, equal sign. I'm selecting A11 because that's where I've described the x variable, and enter. Chart title, equal sign. And I've already created a label up here. And what's amazing about a binomial distribution or experiment is those are the only two inputs. Now I'll hit enter, and there's our chart. Now I'm thinking, let's delete this. I'm going to select it and use the delete key. And very carefully, not that. I want the inside lines. So I select them, use the delete key. Now from the green plus, let's show data labels. And I kind of like that because there's the probability of making 4 sales in 4 tries. Very small. Now we want to calculate mean and standard deviation. And let's first do it the universal way. This method for calculating mean works on any probability distribution. We take the x values in array 1, comma, and then we multiply and add the probabilities. We get a mean of 0.8 policies sold in 4 tries. Now, since this is a binomial experiment and we have a binomial probability distribution, we can simply take n times p, and that will give us the average number of policies we sell in 4 tries. Now, standard deviation, we'll do it the old way where we take inside parentheses all the x values, subtract the calculated expected value, raise it to the second power. That's array 1. We need to multiply and add that with the probabilities. Close parentheses. That's variance. Now, to get standard deviation from variance, we take the square root. And it just so happens that for this binomial experiment, the mean is exactly equal to the standard deviation. Now let's try this formula. Equals the square root n times p times, in parentheses, 1 minus p. And that's our formula when we have a binomial distribution to calculate standard deviation. Now we want to calculate various probabilities using our Binom.DIST.RANGE function. Our first probability is the probability of selling exactly 2 policies. So we get our function. Trials is the first argument. There it is, 4, comma. Probability of success is the second argument. There it is, 0.2, comma. And since we're calculating exactly a particular x, that's all we use. Number s, we'll put a 2 in. When I hit enter, that's the probability of getting exactly 2 sales in 4 tries. Now, how about the probability of having the number of sales made greater than 1? Looking up here, that would be 2, 3, and 4. So the trick is going to be figuring out the lower x and the upper x. So equals, we'll get our function. trials, comma, probability, comma, the smaller x value, that's the first number greater than 1, comma, the upper x is 4. And that's our formula. When I hit enter, we get the probability of selling greater than 1 policy in 4 tries, 18%. What's the probability x is greater than or equal to 3? Well, that means we would have a 3 and a 4. We put in our function with trials and probability, comma, there's the lower, comma, there's the upper. And when I hit enter, the probability of selling 3 or more is about 2.72%. Probability less than 3. That means we have to go all the way to the lowest value. And since it's less than 3, 2 will be our upper limit. Trials, probability, lower, upper, and enter. So the probability less than 3, 97%. Now we're going to see 2 different ways to do x less than or equal to. We'll use our Binom.DIST.RANGE. We have to put the very smallest value in all the way up to 3. So number s, that'll be 0. And the second x, that will be 3. If you ever have to use the older version, Binom.DIST, here's how you'd use it. The arguments are not in the same order. Number successes, that's the x value. And there's only 1 in this function, just 1 number of successes. Comma, trials, that's the second argument. Comma, probability of success, that's the third one. And here it is, the fourth argument, comma, cumulative. If you put false, that instructs Binom.DIST to calculate exactly 3. If you put true, this function always goes from the lowest possible value up to whatever x value you give it. So we gave it 3, so it's automatically going to go from the lowest up to 3 and include all values. So you can either put a true or a 1. We'll put a true, close parentheses, and we get exactly the same thing as Binom.DIST.RANGE. Now, if you ever get into the situation where you have a bunch of uppers and lowers, for the exact probabilities where you're calculating an exact x, you can repeat. So it'll be going from 2 to 2. And then you can actually spill the whole formula. Binom.DIST.RANGE, trials, comma, probability of success. The low x, there they are, comma, the upper x, there they are. And now when I enter, all the probabilities spill. Now, if you have the probability distribution here with all the possibilities, you can use the sum function as we did in an earlier video. So for example, for the probability that x is greater than 1, Alt equals, highlight the probabilities for the variable where it's greater than 1. I'll let you finish the rest of those. Now let's go over and look at our next example, B3. Now here's our experiment. A flight from Oakland to Seattle occurs 6 times per day. And the probability that any one flight is late is 10%. What is the probability that exactly 2 planes are late? Less than 2 are late? And what is the mean and standard deviation? Now, as always, we have to check and see whether the experiment is a binomial experiment. Are there a fixed number of trials? Yes, there are. 6 flights per day. Each trial results in either late or on time, so yes. P remains the same each time, yes. And from one plane being late to the next, those events can be assumed to be independent. All right, so I've listed our variables. N, P, there's one of the x's. And we can calculate mean and standard deviation without any of this other stuff. We have only n and p. So the average number of late planes for one day with these 6 flights is n times p. When I hit enter, wow, 0.6 planes are arriving late. And by the way, this formula makes sense because we're always just counting. And if we have 10% of the planes are late, then what's 10% of the 6 flights? 0.6. Standard deviation, we take the square root, and guess what? Since this is n times p, I already have that right there. So the mean times 1 minus p, close, close. So it looks like we have a standard deviation 0.73 planes. Now we can list all the probabilities for this experiment. We'll list our random variable x sequence. We have 6 flights, and we need a 0, so we add 1, comma, comma. The start is 0. The default step is 1, so when I hit Enter, 0 to 6. Now we can use the amazing Binom.DIST.RANGE. Trials, comma, probability, comma. And here it is. Number of successes. I'm giving it every single possibility. And when I hit Enter, all the probabilities spill down. Now we come to the bottom. They better add up to 1. Alt equals. And they do. And it looks like every single probability is greater than or equal to 0. Now for all of these probabilities, x equal to 2, x less than or equal to 2, less than 2, greater than or equal to 2, and greater than 2, we know with our new function we have to list both the lower x and upper x. Now we could do this one at a time, but if we really want to calculate all these, our function will do it all at once. Oops, I got the wrong function. .range, trials, probability. And here's our lower x that I'm going to highlight from the bottom up since our formula is hanging out on top of our variable inputs, comma. And then here's the upper x. And when I hit Enter, it looks like the probability that there are greater than 2 planes late, 1.5%. Now let's go over to the worksheet B4. Here's our experiment. The probability of getting stuck in traffic on the West Seattle Bridge in the morning is 0.15. Over the next 2 weeks, that's 10 working days, what's the probability that you'll get stuck in traffic 0 times or 1 time? I'm really interested in the 0 time. Now, all of the binomial experiment requirements are met, so we'll answer yes to all of those. There's our n, there's our p, and what's the average number of times we're going to get stuck in traffic? Well, n times p. Bummer, 1.5 times getting stuck in traffic over the next 10 working days. Let's calculate every single probability for this experiment. We use sequence 10 plus 1, comma, comma, 0, and Enter. Equals binom.dist.range. Trials, there are 10. P, 0.5. And there's every single possibility, and Enter. Down at the bottom, Alt equals. And it looks like it adds up to 1, and every probability is greater than or equal to 0. So there's our answer. The probability that we're going to get stuck in traffic 0 times over the next 10 working days, 19%. 1 time, 34%. Now let's go over to sheet B5, and we want to look at an academic example. Highline found that 16% of its students withdraw from Accounting 202. Now, why would you want to withdraw from Accounting 202? That's where you get to do bond amortization, one of the most exciting topics in accounting. All right, in the current class that has 35 students enrolled, what is the probability between 3 and 7 students will withdraw? And what is the mean? Well, we can answer yes to all of these. There are 35 trials, 1 for each student. Each trial results in withdraw or not withdraw. Probability is 0.6, and each event is independent. Now let's calculate the mean. I'm curious. What's the average number of students that will withdraw? There's our n times p, and Enter. Wow, so 5.6 students are going to miss out on bond amortization. And now we do between 3 and 7 inclusive. We use our function. There's n, 35. P is 0.16. The lower x is 3. The upper x is 7. And when I hit Enter, wow, so 75% chance that between 3 and 7 students will withdraw from Accounting 202. Now let's look at our last example B6. Now we want to notice something about a binomial experiment and the binomial probabilities and the shape of the data. And the first thing is, as n increases, the distribution approaches a bell shape. So here we have n equal to 5. I'm going to change it to 10, and we're going to watch the shape of the distribution. All right, we can see it come down a little bit here. 20. Ooh, now it's starting to look more bell-shaped. 30. 50. The shape of the distribution gets more bell-shaped or more like a normal curve. I'm going to change this back to 5. And now let's look at what happens to p. As p approaches 0.5, the distribution approaches bell-shaped. And in fact, exactly at 0.5, the distribution is bell-shaped. Let's change it to 0.2. 0.3. Here's 40%. And when we change it to 50%, that makes sense. If something can go either way 50% of the time, it makes sense that most of the values are going to be right directly in the middle. And in fact, it's exactly bell-shaped on either side. All right, in this video, we talked all about a binomial probability distribution. We made sure to check for the 4 requirements to see if a particular experiment is a binomial experiment. We saw the amazing math formula for calculating a particular x probability. We saw the formulas for mean and standard deviation. We saw the ever so powerful and amazing Binom.DIST.RANGE function. And we even saw how to plot our probabilities in an Excel column chart. All right, next video, we're going to look at another amazing probability distribution, the Poisson distribution. All right, we'll see you next video.